All right, well, thanks very much for the chance to share some of the work we've been working on recently. I want to talk about trying to map the topology of ionized regions at a time when the universe is partially ionized in the intergalactic medium. And I think one of the motivations for doing this is if you find and map ionized bubbles, you can look and see what's inside of them. So part of this is about identifying the galaxies that are the ionizing agents of these particular bubbles, and then studying their properties. So in this case, we're going to look at an overdensity of Lyman alpha emitters, okay, at Redshift 7. So this is a time when, in terms of the global neutral fraction in the IGM at Redshift 7 here, you can see it's about a half, okay? That's the halfway point. You can also see that as the number of measurements has increased, there's a lot of scatter here, okay, between different measurements. And I think the scatter is actually increasing as the data improves, which to me is an indication that there may be significant differences depending on where you're looking, okay, on the sky at this redshift. So things are changing rapidly. So we're kind of in this region. We're going to be looking at a very overdense region, okay, not a typical region of the universe, but one that's selected because there's an overdensity of Lyman alpha emitting galaxies. So the expectation is that it would be ahead of the universe on average and over-ionized. So this is a map of Lyman alpha emitters at Redshift 7 found by the Logger survey. And I want to point out Wei Hu, who's here. This is his Nature paper, discovered this area Logger Z7OD. The full area of it in the black box here has a galaxy overdensity of about a factor of 6 relative to the cosmic mean, significant overdensity. And with James Webb Space Telescope, we were able to pre-image and then do NIRSPEC spectroscopy in the region shown by the red box here. So we're looking at the western part of this overdensity. And this is a map on the sky of the 9 Lyman alpha emitters, okay, that we observed. So we're going to talk about the measuring Balmer, hydrogen Balmer lines with James Webb. The Lyman alpha line profiles that we're going to compare to this come from the LRES spectrograph on Keck. And then we have some NIRCam imaging. So I'm going to start out, I'm going to show you like the result on the sky. If we were just to, on this map, paste the ionized bubbles, what it looks like. And this is what you get from a basic fiducial model here. But I would argue, I think this model is wrong. This is what's typically done where the attenuation of the Lyman alpha is attributed to the intergalactic medium. But the Lyman alpha comes out of galaxies, and in low redshift galaxies, the interstellar medium, okay, significantly attenuates the Lyman alpha line. So one thing we do in this paper is try to use properties of the galaxies and scaling relations from local Lyman alpha emitting galaxies to correct for that interstellar attenuation. And when we attribute some of the attenuation of Lyman alpha to the interstellar gas, that means we need less attenuation from the intergalactic medium, and we end up with much larger bubbles where there's more overlap, okay, between the individual bubbles. So now that I've kind of showed you the result, let me go back and try to explain how we got here. So if this is a Lyman alpha emission coming from a galaxy, okay, the ionizing photons produced in the galaxy, recombination produces Lyman alpha. The emergent Lyman alpha profile from the galaxy, right, is redshifted away from the resonance frequency, either to the red side or the blue side as Lyman alpha scatters around and finds a path where it can get out of the galaxy. But for a very distant Lyman alpha emitter, right, as we're observing it and the gas passes through gas clouds near the galaxy or even megaparsecs away, it looks like the Lyman alpha emitter is redshifted. So anything that was emitted blueward of the line profile redshifts through the line resonance, okay, and is observed, and we won't see that from a high redshift galaxy. And over megaparsec scales, the damping wing of the Lyman alpha profile, which is what's shown here in red, okay, if there's a neutral medium around the galaxy, will attenuate the line. So if the black line here was the emergent profile from the interstellar medium, what the neutral intergalactic medium does is shift, attenuate the line, okay, reduce its intensity. And I'm showing here the different colors are like bubbles of different sizes, okay, where if you put a big ionized bubble around the Lyman alpha emitter, then a lot of the emission can get through, and there's only a little bit of attenuation. And with a small bubble, you would attenuate most of the line. What you're essentially measuring here, okay, is the distance from the galaxy to the first neutral path, this r sub I. So plot it another way, okay? If we think of this as an ionized, if we think of this distance to the nearest neutral path as the radius of a bubble around the galaxy, then as for the radius of the bubble increases, for a given offset from the resonance frequency of the emergent line profile, so pick a curve here, these are different velocity offsets. Okay, at 0 here, as the radius gets bigger, the Lyman alpha transmission increases. But for a larger initial velocity offset, take this curve, right, at a given transmission, you need a much smaller ionized bubble to produce the same transmission. So we're measuring two things here. We're measuring this velocity offset, where the systemic velocity is coming from the Balmer lines, and we're measuring the Lyman alpha Doppler shift from the CAC-L-Res spectrum. And we're measuring the attenuation here, okay, where we've got the Lyman alpha luminosity from the narrowband imaging in an integrated sense. We've got the Balmer line luminosity from James Webb, and case B recombination theory tells us the number of intrinsic Lyman alpha photons. When we multiply by 8.7, we get an escape fraction. So these are examples, okay, of some of the bubbles where basically we're picking the curve that corresponds to their velocity offset, measuring the transmission, and then boom, reading off a radius. And you'll notice there are two sets of points here. Solid points are model 1 with no ISM, the red bubbles, and the open symbols are model 2 with interstellar medium. The half-filled symbols are model 3, which we may or may not get to here. Okay, so here are these are mainly H-alpha profiles. A few of them are H-beta. You'll see in the images later, many of these are clumpy galaxies, so we have spatially resolved spectral information in some cases. And then here are the Lyman alpha spectra. To measure the velocity offsets, we are using the narrow peak here to define the velocity offset. You'll notice that many of these have very broad and extended red wings, okay, due to the resonant scattering. So some of these properties, we can compare them both to other high redshift galaxies and to local galaxies. I'm going to focus here on the comparison to local galaxies because these are what we're going to use to model the interstellar medium. So this is the Lyman alpha escape fraction as defined in the previous slide in the velocity offset. And these are our galaxies in logger Z70D. The black points here, okay, are a study of green P galaxies. Green P galaxies are these compact galaxies selected from their high oxygen-3 equivalent width, okay, at redshifts of a few tenths. Many of them are known Lyman continuum leakers. And in this study by Wan Yang, you can see all the points here. The ones up at the top with the high Lyman alpha escape fractions and low velocity offsets over in this region tend to be Lyman continuum leakers. In a plot of Lyman alpha escape fraction versus the O32 ratio, which is sensitive to the ionization parameter, the number of ionizing photons per unit gas atom, the green P's that are known Lyman continuum leakers, okay, are shown here with the red circles. And they fall in this band of kind of favorable O32 ratios that Nicholas Chustikov's radiation hydro simulations have shown are kind of the sweet spot for Lyman continuum escape. And you can see these Lyman alpha galaxies. Many of our measurements are O3 detections without O2, so some of them are lower limits, but some of them fall in that range. So this Yang sample of the green peas, we're going to use as our basis for modeling the interstellar attenuation of Lyman alpha, because you can see these populations have similar properties, okay? And what he did was basically fit the Lyman alpha escape fraction as a function of the Lyman alpha velocity offset and the amount of dust in the galaxy, the reddening. And the coefficient out here in front has to do with the choice of extinction curve that was used here. There's a 0-point offset that shows you in this empirical fit to the data, there's kind of no limit where the Lyman alpha is not partially, okay, attenuated. Whether this is the right model to use in a high redshift galaxy is not clear, okay, but it's a starting point, so we wanted to see what would happen. So this is the same picture I showed earlier, but kind of from a different perspective, where you can see the bubbles spread out in redshift. And I think it's interesting, they kind of fall into three clumps, this like subcluster structure within the region. And the bubbles individually are kind of approaching overlap. They're not quite there. There's a little bit of overlap here between 10 and 14, and that's it. When we do kind of the minimum correction for the ISM, which our Balmer decrements have large error bars on them, but they're consistent with zero reddening. So if we just use the velocity offset part of that equation to predict the interstellar escape fraction, you can see that if that's a half, okay, then it would increase the transmission of the IGM by a factor of 2. And we need the bigger bubbles, okay, as shown here. And in that picture, there's substantial overlap between bubbles 14 and 10 here, and between, 14 and 1 and 13 and 10 over here. It's interesting, though, in terms of the number of photons required to ionize the bubble, they go up even though there's overlap. The increase in the total volume is larger than the volume that's overlapping there. Okay, so shifting to how many ionizing photons are needed here, we're in a regime where the recombination time, okay, is around 300 million years, which is long compared to the star formation history of these galaxies. And we can ignore on the timescales of the star formation here the expansion of the universe. So we basically need one ionizing photon per hydrogen atom, okay, in the bubble. And that's what this equation, okay, is describing. And then in terms of the number of photons that we need, that's a rate that ionizing photons are produced times an escape fraction, okay, from the galaxy. I don't care if the ionizing photons are produced by stars or AGN. We're measuring them directly with the luminosity of H alpha. We're measuring the recombination rate. And then the intrinsic rate is the Lyman alpha luminosity over 1 minus the escape fraction. And then what gets out of the galaxy into the bubble is F escape times that. So you can kind of make a picture here, right, of how long the star formation or the black hole activity would have to last as a function of the escape fraction to get over to the point where the galaxies are. And the bottom line here is that for some of the galaxies, we're on a part of a track that the Lyman alpha emitter alone, okay, can ionize the bubble around it. And there's other galaxies in the sample where the Lyman alpha emitter alone is not quite enough. If you integrated down the UV luminosity function from, most of these guys are like minus 20 in MUV. If you integrated down to about minus 17, you'd have enough additional galaxies probably to ionize these bubbles. So the Lyman alpha emitters themselves do seem to be supplying a lot of the ionizing photons, okay, that are needed here. I won't go into this too much. We spend a lot of time in this paper talking about the star formation history to try to pin down the parameters of the current burst, but understand the star formation history over a 300 million year time scale. And I'll just highlight a couple things that from the H-alpha equivalent widths, the current burst, okay, are quite short, of order 10 million years. We can compare H-alpha luminosities to UV magnitudes that probe star formation on a longer time scale, okay, up to about 100 million years, and constrain the star formation rate better. In 5 of the brightest galaxies, we've been able to run bagpipes models. We can supplement the JWST photometry with ultravista photometry and get a pretty good UV continuum slope here. These are the star formation histories that came out of the non-parametric bagpipes model. The critical thing here is that the recent burst is supplying most of the ionizing photons when you integrate over this star formation history. There's more time out here, but it's down enough in amplitude that the recent burst is dominating. Determining whether there are any AGN in these galaxies is difficult because at low metallicities, BPT diagrams are kind of degenerate between AGN and star-forming galaxies. There's a nice paper by Mazzolari that suggested a new BPT diagram for picking out AGN. This is the 4363 line, the temperature-sensitive one, against the normal 032 ratio. And it's interesting that one of our galaxies does favor kind of a position that's in the AGN-dominated diagram, although this is a lower limit there, so it wouldn't have to be. But there are some other signatures in these galaxies that, just based on their high Lyman alpha luminosities, these 3 are also potential AGN candidates. So who are these galaxies that are ionizing these bubbles? And these are the NIRCam pictures of them paired up with a REST UV and a REST optical picture. And you can see they're mostly very clumpy galaxies. And we could talk about that a lot more, but I want to wrap up there, okay, by putting this in kind of a summary diagram. So these are the bubble radii. I put them at kind of an arbitrary global neutral fraction here of 1/2, recognizing that there's a lot of uncertainty from field to field here. And to make a comparison here to a model of bubble size by Furlaneto and O that some of you will be familiar with, where they were really predicting sizes of individual bubbles, okay, not accounting for bubbles merging and what those sizes would be. And our individual bubble measurements lie largely on that without correcting for the ISM and getting the larger bubbles. When we correct for the ISM, okay, we're moving up a little bit. Well, that could be still consistent with this model, but a lower XH1, or it could be consistent with the kind of gradual reionization model in Tingley Liu's paper with Charlotte Mason, where they're taking into account and modeling bubble mergers, okay, in the sizes of these larger larger bubbles using a watershed type algorithm. It's not really a limit here, right? We could be pushed up even higher to these half-filled symbols, which was doing the last part of the interstellar medium correction, including the dust reddening correction. So we're not real definitive, okay, in distinguishing between these models, but I think there's potential here of pinpointing, what are the ionizing sources inside a particular bubble, and who are those galaxies? What are their properties like? Are they completely different from galaxies at low redshift, or do they have familiar physical properties? And yeah, I guess I'll just end there, leave the conclusions up.
So, do we have a quick question for Crystal before starting the discussion session?
So when you say that the combination time is very long compared to the system time, do you take into account clamping factors?
For the recombination time? No, just at the average.
Because of this clamping factor of the field, maybe.
Sure, that could make a difference. Yeah.
Okay, so why don't we go ahead and thank Crystal, and then Crystal and Casey will be in discussion.